Thank you for the introduction, Trishan. So, probably this should have gone before the previous talk, but as it happens, this is just life. So my name is Florin Coras. I'm a Cisco software engineer. And just before I dive into this, apologies in advance for those of you who've seen this presentation about 5 months ago at KubeCon North America. Probably I'm going to sound like a broken disc to you, or at least partly. There are several reasons for that, but probably the most important is that over the, let's say, this last 5 months, we've seen a lot of changes into the stack, but they were mainly aimed at optimizing, cleaning up, and reorganizing perhaps the code. So we've had a lot of changes, but perhaps not as many new features added to the stack as we've had at previous presentations. I like to lie to myself and tell me that this is a sign perhaps of a coming of age of the stack and of stability, but rest assured there's still many things under development. So having gone through that, for reasons that mainly have to do with efficiency of container networking, let's say, and when done in combination with VPP, more than 2 years ago now, Dave Barrick, myself, amongst others, we've started work on the host stack. And the one thing that was obviously missing when we started work then was a TCP, or the transport layer, and TCP in particular because it's the most commonly used transport protocol out there to this day. Maybe some shared memory infrastructure to have external applications be able to communicate with the stack within VPP, but nothing beyond that. It quickly became obvious that we were missing multiple components, and in particular, let's say we were missing even layers. And we eventually ended up with something that looks like this. In the interest of time, I guess what I'll do now next is focus on these major components. I'll go into them in a bit more detail. I'll try to cover less ground, let's say, and I'll try to focus on this because from interactions that I've had both with Cisco internal folks and with external folks who are using or are planning to use the stack, I've noticed that some of the things perhaps are harder to follow, so maybe dwelling on them will be better. So without further ado, the first component of the stack is the session layer. This is one of the components that has seen a major refactor over the past 5 months. The focus was mainly on restructuring the code and optimizing somewhat the code, so not necessarily new features. If we look at it at a high level, let's say, the operation that it performs is it acts as an intermediary between northbound applications and southbound transport protocols. And to this end, what it does northbound through the app interface sublayer, it exposes a set of APIs that allows applications to interact southbound with units of communication or abstract units of communication that we call sessions. And southbound, it exposes APIs that allows transport protocols to exchange data and events with applications, but without being aware of how that communication is actually being carried out. Now, focusing on the app interface sublayer, this is the place or the component that keeps a per application state. That is, it knows where the application can be found over the binary API. It knows how it can be found or where it can be found over the session layer messaging API. We'll see in a second that we call that the message queue. And if the application has multiple workers, that is, if the application registered multiple workers for the stack, this is the place where we keep track for them or state for them. And it also maintains, a state that tracks whatever services the application requested from the session layer. It is the app interface sublayer is the one that's responsible for allocating this thing, the greenish thing here, the shared memory resources that we use for application use for communicating with the session layer. And at the same time, it's also responsible for coordinating with these external applications in order to have them find, mount, and eventually use this shared memory resources. And apart from the shared memory API, the app interface sublayer also exposes a native C API. Now this one is used for built-in applications, that is applications then run within the VPP process. We'll go over these in a bit more detail towards the end of the presentation. So now moving southbound or into session layer proper, let's call it, we find that this one offers a set of services. And well, first of all, obviously, this is the place that allocates and tracks sessions. It allocates sessions on a per VPP worker basis. So the session layer is VPP worker aware. And then it looks up sessions using per IP fib table 5-tuple keyed session tables. So the normal way one would look up flows. The session layer exposes, let's say, a generic template that transports need to fill in and then use that to register themselves as a transport with the session layer. And it also provides, let's call it a base class for the basic unit of communication from a transport perspective. We call that the transport connection. Now those connections, the transports can extend, so it was a base class, they can extend, and then whenever interacting with the session layer, the transports have to use that sort of objects. And finally, the session layer can provide isolation of network resources, and network resources here are like IP fibs via something that we call application namespacing. And for instance, if an application is configured to use a given namespace, a given application namespace, it can only connect or receive connections within that namespace or using its own specific IP interface or network interface, let's say. Now, if the app interface was the one component that knew how to talk with external applications, the session layer is the one that knows how to interact with transport protocols southbound. So it exposes APIs that allow those transport protocols to exchange messages on the one hand, and on the other hand, to exchange data. That is, it has APIs that allow transports to enqueue data towards the applications. Now, from a transport perspective, data typically means I/O buffers or bytes within I/O buffers, whereas from application perspective, data means streams of bytes or, in some cases, datagrams. Now, session layer is the one that knows how to convert from one representation to the other. In other words, it accepts I/O buffers from the transports. It knows how to enqueue those into shared memory buffers. We call these buffers FIFOs. And then the applications can read the data out of these FIFOs. And it knows how to do the converse operation as well. So if applications write data into the transmit buffers, the session layer is the one that knows how to read that data, segment that data into I/O buffers, and then present the I/O buffers to the transport protocols. I guess it's obvious from this that all the sessions have a pair of FIFOs associated to them, or buffers shared memory buffers associated for them for receiving and for transmitting data. And talking about sending of data, recently, well, I guess some less than 6 months ago, we've added the feature to the session layer to enable it to do TX spacing. And by that, I mean whenever a transport requests that the session layer starts pacing its data, the session layer, when it reads the data from the transmit buffer, it actually paces the rate at which it creates I/O buffers before injecting them into the transport to ensure that we avoid TX bursting. And this is especially important even for transport protocols that do their own congestion control algorithms like TCP, because they can still burst at very short timescales. So in particular for TCP under RTT timescales. And with that, we're moving to the second component of the host stack, which is the shared memory tooling or infra that we've built on top of VPP's SVM library. Now, the basic blocks here are I/O buffer, our shared memory segments. We have two types of shared memory segments. Traditional POSIX shared memory segments, these require file system backing, and we have memFD shared memory segments. As the name suggests, in this case, we have a memory FD that's allocated by the stack. We exchange that over the binary API's socket transport, and that way the application can find the segment and use it. Now, because memFD segments are much more secure than the traditional POSIX-based shared memory segments, and because they're easier to use in practice, they impose no constraint on some file system resource being available and shared between the application and VPP, probably will end up, well, for sure will end up eventually deprecating the traditional POSIX segments. Now, within these, we allocate two types of data structures. First up, message queues, which obviously are used for exchanging messages. By convention, we allocate these message queues in the first segment that's allocated for an application's worker. So if an application, for instance, has multiple workers, each one of the workers in the application will get a message queue, and those message queues will be allocated in the first segment allocated by the session layer for those workers. The message queues have two rings, one for I/O events and one for control events. We do this separation because I/O events are much smaller, fixed size, and they're much more prevalent compared to control events. Therefore, we can optimize the geometry of the message queues much better if we do the separation. And another very important thing here is that message queues support both blocking and non-blocking enqueuing and dequeuing of messages. Whenever blocking operation is requested, the consumer and the producer need some form of signaling to signal the transition from empty to non-empty state or from full to non-full state. And for this, the message queues can use actually two mechanisms, a mutex convar pair, or they can use event FD. And the reason why I'm mentioning this is if applications, well, although event FDs are slower than convar mutex pairs, or at least in my testing, they're interesting because if we have applications that want to do both Linux FDs and VPP sessions at the same time, then if they use event FDs for signaling, this happens to be pollable, so you can add them to an epoll group, you can do select on them. So they're much easier to use for this type of applications. The second thing that we allocate within the shared memory segments are the SVM FIFOs. We've already seen what those are. Well, we don't allocate them directly in the segment. Instead, we wrap the segment into a new data structure, which we call a FIFO segment. That's just a data structure that has logic that optimizes FIFO allocation. Both the FIFO segment and the FIFOs have seen major improvements over the past 6 months. They're aimed both at efficiency or speed, in case of the FIFOs, but they're also aimed at adding more features. In particular, FIFOs were fixed size and position. Now they're growable, they're dynamic. And if before they were fixed size, now only this holds true only for the header. The header is fixed size, it's very small, it's just 4 cache lines, and it can be anywhere in the memory in a FIFO segment. However, the data part is no longer contiguous with the header. So that means now instead of having data just after the header, we have a linked list of memory chunks where data can be stored and from where it can be retrieved. There's no restriction on how big those chunks are, although here I'm showing them all of the same size. They can be any size. And there's no ordering constraint either. They can be anywhere in memory. The list gives us the ordering. Important thing here, though, is the list can grow and can shrink, and that's the feature that we're looking for. So apart from that, the basic service offered by the FIFO is lock-free enqueue and dequeue. And now because the producer and consumer are obviously in different processes, we need some atomic operations. An important feature that, or an important addition, a recent addition, is the fact that ARM, with the help from guys from ARM, Seychak in particular, we're no longer storing the FIFO size within the FIFO header. So when we have consumers and producers, they no longer compete for this shared resource. Instead, we compute the size dynamically within the consumers and the producers. Apart from the basic service that they also offer service for transport protocols like TCP, so reliable transport protocols, and those are out-of-order enqueues. So the FIFO knows how to handle those, and out-of-order reads or data peaking in the future. Next up is the third major component of the stack, which would be the transport protocol. Now, in the interest of time here, I'll be focusing only on TCP because this was the first one that we did and arguably the one that's most optimized. Still, it's worth taking a break and saying, at this time, we support or we actively maintain 4 transport protocols. Apart from TCP, UDP, TLS, you saw already a presentation from Ping, and recently since last release we have basic implementation for Quick as well. It's still under heavy development, but the guys have done a tremendous job in a very short amount of time. But now coming back to TCP. TCP is actually clean slate implementation. We started from pretty much nothing, and we try to optimize it for VPP with the goal here of getting the maximum possible performance. From our perspective, or to the best of our knowledge, this is a complete implementation in terms of features, in that it implements what the main standard track RFCs require from a state machine implementation perspective, connection management, and flow control. We do options that are needed for high-speed TCP connections. So we do timestamps and we do selective acts, and we have a highly scalable timers implementation. So we can do tens of millions of connections. In terms of congestion control algorithms, we do now New Reno and Cubic. Cubic, I believe, is also a rather new addition, less than 6 months ago, and we hope to even add newer congestion control algorithms here. We do New Reno-based and selective ACK-based fast recovery, and TCP is probably at this time the only transport that knows how to use the pacing feature offered by the session layer. So it does that in order to minimize, again, its own TX bursting at very short timescales, so under RTT timescales. We only have support for checksum offloading in terms of hardware acceleration, so no TSO, LRO, or GSO, GRO. Nonetheless, as you'll see in a second, I don't believe that at this time this is limiting for us. And for the past 2 releases, we've been doing protocol correctness checks and robustness checks for the whole of the code using a tool from Defensix or from called Defensix Codenomicon. So just to give you an idea, I think for the previous release, we were compatible with something like 1 million tests, and we have a failure rate for those tests that's similar to that of the kernel, which is, I think the order of magnitude is 1 in 10,000 or something like that. So we had a couple of hundreds at most of failures. And with that, we are moving to the fourth and last major component of the stack, which is the comms library, or VCL. Now, this being a library obviously is not part of VPP. However, we have no restriction on apps actually needing to use it to interact with the stack. They could interact with the raw session layer APIs. The reason why VCL exists is because we wanted APIs that were POSIX, well, similar to, but not really POSIX compliant. So just to ease the life of developers. Still, in practice, at times it may make sense not to use VCL. So the developers need to be aware of the fact that if they take this path, they need to manage the interaction with the binary API, with the message queue by themselves. They need obviously to maintain per session state, and in case they want to do multiple threads, they even need to make sure that they do implement the proper locking strategy on top of the sessions. And if they so require, they will need to implement their own async communication mechanisms, and think here about epoll, select, or poll, for instance. Now, for all those cases, when application developers, or maybe almost all of those cases, when developers don't want to be bothered with that, we have VCL. VCL manages the interaction with the session layer. It abstracts sessions to integer session handles, and it exposes its own implementation of the common async functions, and it supports multi-worker applications. Now, the big thing to note here is that applications must manually register their workers with VCL, and they must ensure that those workers are not sharing sessions. This is very important. It's a threading model that's similar to the rest of VPP, but sometimes it's restrictive from the point of view of existing applications. And I guess it's worth noting here as well that VCL can work with MQ notifications with both mutex convar and event FD signaling. Now, for situations when an application cannot be changed to ensure that multiple workers share a session, or if an application has multiple threads and now those threads cannot be registered as separate workers, we have a layer, another shim layer that we call VCL locked sessions, or VLS. This is new, it's rather recent, probably yet again the last one or two releases. As the name suggests, VLS tries to enforce several things via locking, and those things would be, it tries to make sure that only one worker has access to a session at a given time. So if they cannot share the sessions, but if they share, we will automatically lock. And if an application has multiple threads, and obviously those are not registered as separate workers, then well, we enforce via locking. We make sure that only one of those threads interacts with VCL and with the message queue. Now, to note here is VLS detects threads by itself. However, because it cannot tell exactly how those threads will share sessions and how they will interact with VCL underneath, it cannot register them as workers. In contrast to that, VLS does detect forking of an application, and whenever an application forks, VLS will register the child as a separate VCL worker. And finally, this brings us to the fourth shim, well, the next shim layer, which is LDP. Now, for those situations when an application cannot be changed, or changing it is deemed too difficult, we have the LDP shim. This one uses LD preload to intercept syscalls that should be executed in the kernel, re-injects them into VLS. Previously, this was going into VCL, so now it goes into the locking layer. You've seen Ping's presentation with respect to this. When it works, it actually works seamlessly from an application perspective. They just work seamlessly with VLS. No code changes needed, but obviously the big star in the margin here is don't expect LD preload to always work. It won't work for statically linked applications, and most probably we do not support all the syscall combinations and all the syscall options, and combine those with now threading behavior and forking behavior, everything gets complicated. Nonetheless, having said that, we do support some commonly used applications, and recently we've tried to get them to work as best as possible. Things like iPerf, for instance, Nginx or SSHD. However, keep in mind that if we want to extend LDP at one point or want to harden all the shim layers that are underneath to work with multiple applications, this needs to be done on a per app basis. Although it sounds absurd, and a quick rant here, things like, for instance, supporting SSHD means making sure that if an application wants to fork 4 to 5 times to accept a new connection or a new SSH connection, because authentication is that complicated in that situation, obviously debugging and making sure that everything works properly is rather difficult. On the other hand, we have the Nginx example, which follows a threading model which is relatively similar to that of VCL, but suddenly decides that it wants to share all the listener sessions, or in Linux terminology, sockets, across all the workers. Obviously, that suddenly complicates our life a lot. So again, supporting multiple, more applications, it's actually relatively involved. I guess after a certain point, it gets easy, but until we understand all the patterns, it's rather difficult. Now, let me stress it again, as stressed during Ping's presentation, LDP has not been optimized for performance, so not for throughput, not for scale. It has only been implemented for functionality, let's say. And speaking about throughput and performance, this is typically how the way we measure performance or throughput speed. That sounds funny. I typically use 2 machines, a VPP to which we have an attached server, and a VPP instance to which we have attached a client, and a high-speed, low-latency network between the 2 of them. Now, I won't go again over all the details, but the messages and the exchange of data follows exactly what we've discussed until now. But in my testbed, so that means with servers that are Broadwells running at 2.2 and 3.2 gigahertz per second, and using Intel XL710 NICs, so 40 gig NICs, and running iPerf as an application on top of the stack. So we take the cost of LDP in this case. We can do about 36 gigabits per second per core, 1.5K MTU, and obviously in half duplex mode here. So again, LDP, in some situations, it's not a slowdown for the performance. Nonetheless, that doesn't mean it will work always. It doesn't mean the stack will work as well for all types of applications in combination with LDP. And also, I'm mentioning here the what the CPUs are, because obviously it will vary a lot in your testbeds if you use different types of hardware. And finally, in what time remains, I want to touch upon two more things. Redirected connections, which we call cut-through connections. So what happens when we have a client and a server and they're attached to the same VPP instance? Well, previously what we did, we used the app interface as an introduction mechanism, and then we allocated some shared memory resources, and we let the 2 applications duke it out and exchange the data as fast as possible. What we're trying to do now is we're trying to pull some of that logic into VPP, and that logic converted into a special sort of a transport protocol within VPP. We call that the cut-through transport protocol, and this one knows how to do the introduction between the client and the server. It knows how to allocate shared memory resources for the two of them. So it allocates a segment. Within the segment, it allocates FIFOs. And note how we don't allocate any more message queues. Instead, the I/O and control events are always exchanged by the applications, the client and the server, with VPP, not amongst themselves. And in this sort of a situation, depending on how we want to measure performance, if the applications do not touch the data at all, we can go as high as 120 gigs per second. If we use iPerf with LDP, things are a bit less efficient because we have 2 mem copies. So we copy into the FIFO, then iPerf copies the data from the FIFOs into its own buffers, and only afterwards it drops it without touching it. So in that sort of situation, we manage somewhere around 90 to 100 gigs per second. And finally, as I promised originally, VPP built-in applications. That is, applications that run within the VPP process. Now, these ones obviously will use the C APIs of the app interface as opposed to the share memory APIs. When they attach, when this application attached to the stack, they provide a set of callback functions that should be called on I/O and control events. And the share memory segment where FIFOs for the sessions associated to this built-in applications are allocated, is actually allocated within process memory. However, this is known or understood only by the underlying shared memory infrastructure. From the point of view of the rest of the system, they look just like normal segments. And obviously with this sort of an architecture, control and RX I/O events are delivered to the app via callback functions within VPP worker context. That is, although the application itself thinks it's single-threaded, it actually receives calls on multiple VPP workers, so some care needs to be taken there. But for sending data, the TX/IO events, they work exactly as they work for external applications. So we just use the session layer APIs. And if you're curious about how this works, we have several examples. Probably an interesting one, a cute one, is the HTTP static plugin. This is something that they've built, and it can serve VPP. It's an HTTP server that can serve VPP's internal documentation. And we also have a set of echo apps, we call them. It's, let's say, ping a transport layer. They know how to work with several transports, and we use them for protocol testing and for sometimes for throughput testing. So if you want to know more about the stack, here are some pointers. And with that, I'm done. Thank you very much for listening, and I'm ready to take questions if we have time. And I think that's a sign that no.
Yeah, maybe one question.
Go for it.
On the internal apps that you just last mentioned, how would they load? As standable loadable objects like everything else? Or?
You'll have to excuse me, for some reason the sound is awful. I cannot understand. Can you repeat?
So for the last set you just did, are they loaded via a shared object like everything else? Or is it something else for the built-in apps?
Yes. What's with the built-in apps?
How are they loaded?
They're loaded, so you can use VPP's internal APIs to load those applications. So they can either start when VPP starts, or you can have special APIs that starts those apps within VPP. Oh, no. They actually run within VPP. So for instance, think of them as a graph node, but they're not graph nodes.
So it's more talking about when you add graph nodes as a plugin.
Fair enough. When they're plugins, they're loaded as shared as SOs. When VPP starts, it finds the list of plugins, and it DL opens those plugins and consumes them. So this is how you would start. But actually, your app could be loaded this way, but it's not necessarily started. So you can have APIs to start your app or stop your app. And I think it was...
Yeah, a very short question about TCP pacing.
Yep.
How do you compute the pacing rate? and how do you pass it to the underlying TX?
Very good question. So for pacing, what we do right now, that doesn't necessarily mean we're continuing to do this. Based on the congestion window and the estimated RTT, we compute what the maximum rate at which a given TCP connection could send. So that information we input into the pacer, and we ask the session layer to not let us send faster than what we computed. So it's going to be dependent on what congestion control algorithm computed and what we measured in terms of RTT. Make sense?
Yeah, it makes sense. And so the underlying layer, does it send packets based on how many transmitted packets to the line? Is this is this real pacing, or is it an average kind of pacing?
Okay, so we do not have any scheduler. We don't do anything like FK Codel, if that's where the question is going. Instead, what we're doing is the session layer will not allow packets to be consumed from the FIFOs faster than the rate that we established. So in other words, we keep them in the buffer. We keep, yes. It's only peak rate.
Great. Thank you, Florin.
Thank you.
Thank you.